Good evening, everyone. Thank you for joining us tonight with Perry Hanavan, who will present a consumer-friendly recap of the HLAA 2018 Research Symposium, Listening in Noise. Thank you very much for joining us tonight, Dr. Hanavan. Before we get started, I just want to thank Donna LeCarry from Alternative Communication Services for providing CART this evening. Perry is going to present for 30 or so minutes about the symposium, and then I can take your questions if you would just be kind enough to post your questions in the Q&A. I probably won't be responding so much to the raise hand feature of Zoom, so if you do have a question for me, you can either post it to me in the chat or in the Q&A. All right. Thank you so much, everybody, again, for being here tonight. And Perry, I'll let you get started.
Well, welcome, everybody. This is exciting, and it was exciting to have the research symposium on listening and noise. It was perhaps a little bit complex in some of the presentations at times, so hopefully I can kind of, in this webinar, provide information and make it a little bit more understandable. So I'm not in Sioux Falls right now. I'm actually a little bit south of Denver. So welcome from Colorado. So I'm going to start right off with a few just items about listening and noise. It's sometimes referred to as the cocktail party problem, and many of the researchers referred to this issue of listening and noise as the cocktail party or the cocktail noise problem. And it's that problem of trying to, select the speakers you're trying to listen to from all of the background noise. And so this cocktail party problem is exacerbated to some extent with hearing loss, and even a number of people with normal hearing have problems listening in noise. And I'll maybe talk a little bit about this hidden hearing loss. Our common audiometric tests do not detect what has recently been referred to as hidden hearing loss. And so people with hidden hearing loss do have difficulty hearing in noisy situations. So, so for some of you, it is really difficult listening. And for some, it may be impossible to listen in noisy situations. And some of us just tune out when we find it extremely difficult to hear in these situations. So by the cocktail noise problem, what we really mean, it's background sounds filled with voices, perhaps background music, other sounds, maybe clinking glasses, dishes, and all of those different kinds of sounds that might be occurring. And for most of us, the brain has a natural ability to filter out background noise and make it relatively easy to focus on what we want to hear. But for some, that's not the case. So, so we have a pretty good understanding of how the hearing mechanism processes sounds. In other words, how the outer ear, the middle ear, and the inner ear, and to some extent the auditory nerve function and process sound. But we have an incomplete understanding of how the human brain processes sound, including speech and in conversations. So our speakers were composed of the following: Dr. Andrew Oxenham from the University of Minnesota, and he is the director of an auditory perception and cognition laboratory in the Twin Cities. And then we had Dr. Evelyn Davies-Venn from the University of Minnesota. She was unable to attend, but she had a slideshow which she provided audio, and so it was almost like she was there, you just couldn't see her. She is the director of the Sensory Aids and Perception Lab at the University of Minnesota. Dr. Ehrman Lee was previously at the University of Minnesota on a fellowship, postdoctorate fellowship doing research, and but he has now taken a job at St. Olaf College, a great liberal arts college in Minnesota. And then we had Dr. Duyang Wang at Ohio State University, and he is the director of the OSU Perception and Neurodynamics Lab. And then a final speaker was Nima Meskarani from Columbia University, and I made a mistake. I need to correct that. He is at Columbia University, and so I'll get that corrected. I apologize for not seeing that earlier. So the first presenter was Dr. Oxenham, and he primarily discussed the peripheral hearing mechanism. Now, what I mean by the peripheral hearing mechanism is the outer ear, the middle ear, the inner ear, including the cochlea and the balance mechanism, and the auditory nerve. And so he did not focus on how the brain processes speech. So he primarily discussed in how the hearing mechanism, the peripheral hearing mechanism, encodes sound for the brain to interpret. And so one of the things that he focused on was hearing loss results in the cocktail, exacerbates the cocktail noise problem. So most individuals, hearing loss is not in the outer ear or the middle ear. Most people have the hearing loss that involves the inner ear, specifically the cochlea. And he also discussed hidden hearing loss, and I'll focus on that in just a little bit in more detail. So one of the things that he showed in his slideshow, and I use this when I talk about part of the inner ear function, specifically the cochlea. He showed this animation, and I'm going to show a part of this animation here. What this is we have a number of membranes in the cochlea. And the cochlea, as you know, is kind of coiled up, kind of like a snail. And so this is unrolling the snail and part of the membrane so that it's a flat, on a flat surface. And so you can see that there's, well, let me just play this. So there's the outer ear and the middle ear, and there's the cochlea scrolled up like a snail, and there it's unrolled. And then inside there's this membrane. And I hope the sound comes through. It may not come through. Oh, here it comes. Stop it there. So you can see that this membrane is kind of laid out like a piano keyboard, and in parts it responds better to high tones and parts to very low bass tones. And so this is part of this processing that takes place in the inner ear to send information to the brain for the brain to interpret. One of the other things that he showed is we have two different types of hair cells in the inner ear that sit on top of that basilar membrane that you saw and listened to. And so we have two types. One type is the outer hair cell, and the other type is the inner hair cell. Now, the outer hair cell can actually change size, and this happens when you listen to soft sounds. And so I'm going to play a little bit of this. He played this to Rock Around the Clock by Bill Haley in the Comets. I think I have a Spanish version here that I'm going to just play part. So you can see it's changing, it's getting longer and shorter. So a beautiful tune there. And we call this motility, where it's changing shape. And you can see it's kind of looks like a long tube. And this picks up the soft sounds and kind of amplifies these very soft sounds, and which then transmits this information to the inner hair cells, which then transmit an electrical code to the brain. So the other thing that he talked about that's maybe seems a little bit complex. Now, remember that outer hair cell that you looked at. Now, we have about 30,000 hair cells in the cochlea, and each one of these hair cells is very finely tuned to a very specific tone. And so, I don't know if my pointer works here, if you can see the pointer, but you can see that here, this hair cell is very finely tuned right here to a very specific frequency. But what happens, you can see here, when we have these hair cells get damaged, you can see the tuning is less here. You can see it better here. It's not as finely tuned, it's broadly tuned. And so this is part of the problem why you have trouble hearing clearly, but it's also part of the problem why you have trouble hearing in noise. It's harder to filter out specific sounds that you would like to hear. So a little bit about hidden hearing loss. So this is kind of connected to damage to the outer hair cells. One of the causes of hidden hearing loss is damage that occurs in the auditory nerve. So, we have to connect a nerve fiber to that hair cells to transmit that information to the brain. Well, we call these synapses. And when these synapses don't work properly, they lose their connectivity. It's sometimes referred to as synaptopathy, but it loses some of its connection. So not only do we have damage occurring in the inner ear, but into these outer hair cells and inner hair cells, but it also creates problems with the connections. And so we have some problems that exacerbate this problem of listening and noise. Now, so how does this hidden hearing loss occur? There's several different factors. One is from noise exposure. So I grew up on a farm, drove tractor, and I do have a little bit of trouble hearing in noisy situations, and that's probably due to the fact that I've had a lot of noise exposure. As we age, the synapses do not function quite as well, and then this really creates a problem when we're trying to listen in noisy situations. The second speaker, and as I mentioned, she was unable to attend, but she did have her slideshow and a recorded session. And one person said, "We couldn't see her standing up at the podium." Was she very short? But she was unable to attend at the last minute, but we did get to hear her presentation. Now, her research focuses on hearing aids, implants, and hearing and noise. And as she mentioned, and as we know, hearing aids and cochlear implants primarily improve audibility. So, they can increase the intensity, and maybe we can hear some frequencies that we didn't hear before. But sometimes increasing clarity of hearing is not always improved with hearing aids and cochlear implants. So some of the things that she talked about, that some of the technologies built into hearing aids that can help us hear in noisy situations is, number one, the use of directional microphones. Now, almost all hearing aids and the cochlear implants now are coming with directional microphones. In other words, they focus in a specific direction. And they're not omnidirectional, picking up, sound equally from all directions. So if we're trying to speak to a person in front of us, that microphone will kind of focus on that person. So that's proven technology that helps us hear better in noise. Digital signal processing. I'll talk a little bit later about this, but digital signal processing is where the hearing aid is trying to subtract noise from speech. It helps a little bit, but it has some problems. Another technology is digital adaptive signal processing. So, for example, if we're listening in a group conversation at a table, by adaptive, the hearing aid will detect that a person to our right is maybe speaking louder, and it will focus the directional microphone on that speaker. And then if the different speaker on the other side speaks, it'll adapt and turn the microphone directionality over in that area. So that technology is helpful for some. Another technology that many of you may use, and this is what I like to speak a lot about, is remote microphones and hearing assistive technologies. So this is a great technology that's helpful for many. And then most of our hearing aids now have connections to smartphones and have an app that can adjust the hearing aid, tune it up a little bit in the higher frequencies, take out a little bit of bass, maybe make it easier to hear in noise in certain situations at a restaurant, for example, and then we can adjust it when we're trying to listen to the TV. So these are some of the strategies that she talked about that are some of the technologies that we now have. The next speaker, which Dr. Ehrman Lee, who I mentioned is now at St. Olaf College, he presented his research from two studies that he was involved in. The first one he talked about was a parasitic fly study. In other words, this is a fly in kind of the southern part of the United States that some of us have to deal with, and it's unique because it has the most accurate directional hearing of any animal. And from studying this parasitic fly, it inspired the development of the directional microphone. Now, its hearing mechanism is very interesting. It has two hearing mechanisms, but the eardrums are connected together. So this kind of limits some of the abilities of the fly. And his study, they documented that noise, such as cocktail noise, distracts the fly from being able to find the, say, the back of a cow or a human face to land on. And so if there's noise, it loses its sense of direction. in locating the target. So that was one of the studies he presented on. But so you know, animal studies are very important because sometimes they help us discover new technologies or new ways of developing computer programs that might be able to help us here. And I'll talk about that in just a little bit. Now, the other study, this is kind of the love story that I wanted him to present specifically on. And as you know, there are several different kinds of tree frogs, and one of them is referred to as Cope's gray tree frog. And there's frogs that are very similar that are also tree frogs, but they're a little bit different. But so how does a female on a nice spring evening, listening in what I call the din of noise, to calls of countless male, hopefully Cope's gray frogs, and other noises, that are out there in the environment, how does it find her perfect mate? Well, researchers know that male calls include both the high and low frequencies changing in loudness. So when it croaks, it croaks with a high frequency sound and a low frequency sound at the same time. Now, so female frogs are able to detect the simultaneous changes in these frequencies from noise. So kind of what he did in his study, he had two parts to his study. So the first part of this love story is he devised several different sounds. One, he took out one of the simultaneous frequencies, either the low frequency or the high frequency, and included that with noise, and presented that to frogs in his research lab, and the frog was unable to accurately identify a Cope's gray tree frog male, a good male. And so what they kind of proved from this, the frog brain has this ability to do statistics, and when it hears both the high frequency sound and the low frequency sound at the same time, it has an ingenious mechanism in the brain that kind of filters out some of the noise so that it can hear that perfect female, that perfect male that she wants to find. Now, the second part of the study. So, and this is a little bit of evolution, but the female wants to, identify the frog that is making the most croaking sounds as well as the loudest croaking sounds, because this probably represents a stronger male. And the female wants to obviously mate with a strong male so that she can have good offspring. So that was the second part of the story or study, but kind of a little bit of a cute story, I think. But he was able to prove how these female frogs were able to detect in noise and find, the ideal croaking sound from the ideal frog. And so this research findings might be able to be built into hearing aids and cochlear implants in the future. So who knows where this might lead. Our fourth speaker was Dr. Duyang Wang from Ohio State University. And engineers for years, electrical engineers particularly, have tried and failed to achieve removal of noise from speech. And they've been able to do this to some extent. Using a voice activity what's called a voice activity detector, to identify gaps between people's utterances. In other words, so if I stop speaking for a little bit, or when I pause, or between some of the speech sounds I make, this probably represents noise. And so these kind of voice activity detectors identify the gaps between my speech when I'm not speaking. It thinks that's noise, and it tries to subtract that noise from the speech, leaving ideally noise-free speech. Well, it in theory seems to work, but ideally it really doesn't work that well. So we call this spectral subtraction, is the technical term, and this technology is used in many hearing aids. That's what I referred to earlier as digital noise reduction. It's trying to figure out what is noise, and trying to subtract that background, those background sounds out from the speech. But too often it removes either too much speech or removes too little noise. It is somewhat helpful, but it's not as helpful as we'd like it to be. So in 1990, Dr. Bregman, a psychologist, proposed that the human auditory system organizes sounds into distinct auditory streams. Now, you can see the picture over here with the police car in the siren and two people talking, and then we have a dog barking. These are called auditory streams, and our brain and our ear is able to tell the difference. Oh, that's a siren. Oh, well, that's people talking. Oh, that's a dog barking. Similarly, if we're listening, we go to a concert and we're listening to an orchestra or a symphony. Most of us can detect, oh, that's the violins. I think that's the saxophones. That's a trumpet. So we can hear these different distinct auditory streams. When we're listening to these sounds or these auditory streams, sometimes they are referred to as scene analysis. So, think about that. If we look at a picture, we can analyze the scene. Well, our ears and our brain does the same thing with sound. We can usually detect, different auditory streams, what Dr. Bregman refers to. So this is kind of a theory. And Dr. Oxenham does a lot of research in this area of scene analysis. But anyway, Dr. Duyang, thinking about that theory of scene analysis and auditory streams, created a speech filter. And he was the first one to do this. It was designed on the principle of auditory scene analysis. In other words, to detect speech streams from noise. And he was successful for increasing the speech signal from noise, much better than what the previous engineer attempts had been able to do. However, this only kind of worked in the lab under certain circumstances, and didn't work, in the real world. So he kept working away, and and he provided probably the most technical talk, and hopefully I can make this understandable if you were present at the research symposium. So he built a machine learning program. Now, what do we mean by machine learning program? Machine learning program is a part of artificial intelligence. And so these are computer programs, and some of these artificial intelligent programs have been able to beat the best chess players and other game players in the world. It's been able to learn after several attempts of playing with a person. it's been able to outplay them consistently. Now, so that's one part, machine learning. That's one of the types of artificial intelligence. And now a second component is neural networks. And you can see a picture of this that I've included here. And so neural networks are kind of modeled on actual neurons in the brain. And we pretty much know that this is kind of how we learn new tasks, such as how to swing a bat to hit a baseball, or to play a musical instrument, or to make new speech sounds, for example. We have neural networks in the brain that kind of learn, and so we get better with practice. And so this is neural networks designed, which are really computer programs, and they are making all sorts of decisions. Well, I think I heard that's noise coming in here. Oh, that's this person speaking here. This might be, that's the TV going, for example. And it learns, these different categories of sounds, and then it does some filtering, and it does some further processing. And then it makes some decisions and does some more processing. So he built a very complex training process using these two concepts, machine learning and neural networks, to listen to speech and filter out noise. Now I'm hoping I can get his some of his samples to play. Now this, I don't know if any of you have Alexa or Google Assistant or Siri or Cortana at home. And most of us have some of these on our smartphones. And if we could speak into the microphone and order a pizza, or order something, online. And so these systems are getting pretty good. In fact, they're getting as accurate at identifying words as humans. These devices have 95% accuracy for words. Well, this is some of the complexity that's built into this device. So this gives you an example. This is using artificial intelligence and machine learning to pick up your voice and follow commands, for example. So to kind of summarize a little bit of the model that Dr. Wang has developed here, is he can place, noisy speech with a lot of background sounds into a filter here, and it's making decisions. So is that noise? Is that speech? So he plays it in, and these neural networks are making decisions and filtering out, can actually figure out, oh, that's noise. Oh, that's a person's speech. I want to focus on that. And so then and it's kind of covered up here. I don't know if you can see it, but it comes out, it cleans up takes out the noise. And so he has developed a pretty good system. Now, I got an article that if you want to kind of read a little bit more that he wrote that kind of summarizes his work here. I'm going to click on this. Now, I'm hoping this really doesn't mess me up too much. And I'm going to go to this article and see if it comes up here quickly. If not, I'll move on given time. How am I doing on time here?
I think you're doing just fine.
I've only got one more speaker to talk about. I'm going to move down here. At the bottom of this, I'm going to play a sample that he played. All right. So the first part of this, I should have covered this up. The first part is, this is what is said. So the first part is trying to hear this in speech. So, and then the second part, his computer program, his deep learning machine filters it out. And so let's listen.
The man called the police.
Now, some of you with hearing loss, that still may not have been good, but I couldn't detect this sentence at all in the first part with all of that noise. With his device, he's able to get rid of most of the background noise. I'll play another one here.
It's getting cold. It's getting cold in here.
Yeah, so that's amazing. Now, so he has a mother with the hearing loss in China, so he's been working on trying to develop the technology to help her hear better, particularly in noisy situations, for years and years. Okay, now I'm hoping oh good, we're back, but I think, okay, I'm going to expand this. Hopefully I hit the right button. Oops. Yeah. Okay, there's where I wanted to be, and I've got too much showing here. There we go. So I need to advance forward here if it's going to cooperate. Let's see.
I think you just want to go back to present mode, right?
Yeah, let's see. Why am I not seeing that? Oh. There. I'm in the wrong, I was in the wrong thing. Present mode, let's see. Why isn't that showing up here? Apologize here. Hang on 1 second. Let's see. It should appear on the screen here. Why isn't that showing up? Well, there we go.
There you go.
All right. So the final speaker was Dr. Nima Masgarani from Columbia University. And his research is a little bit different than Dr. Wang's. Dr. Wang, as you remember, kind of his research is based on this theory of auditory streams, and he's developed a model based on that. Well, Dr. Masgarani's research is about how does the brain actually process acoustic signals. So he's, in a sense, attempting to reverse engineer human sound processing in the brain into machines and computers. And so potentially to develop new systems and devices to help persons here with hearing loss better. So initially he devised a method to reconstruct sounds the brain listens to and which it ignores by measuring human brain waves. He actually, so this is what we sometimes do. We just totally tune out when we're listening to cocktail noise. So what he did, his first study, he used volunteers undergoing brain surgery. And he had them during surgery listen to sentences spoken by different people simultaneously. So several people speaking at the same time while measuring their brain waves. And he fed these person's brain waves into a computer algorithm that his lab had developed. And the computer was able to reproduce the words that patients were, oops, that should be played, I didn't catch that, played, that they, paid attention to while ignoring the other speech. So he discovered the brain is able to filter messages. So when I want to listen to a speaker and kind of ignore the other, my brain kind of turns up the sound of that speaker and kind of reduces the sound of the other. Well, he wrote a program that was able to kind of reproduce this. So his computer program could essentially translate a person's auditory brain waves into real words. Now, I couldn't find the sound recording. He actually hooked up electrodes to the brain, and he was able to decode this coded message in the brain. Now, basically the message in the brain is just clicks. And he was able to take all those clicks with his computer program and decode it so it sounded just like the person was speaking out of the brain. So this laid the foundation, his research laid the foundation to brain-machine interfaces. So the next study, he used speech samples listened to by persons undergoing clinical evaluations for epilepsy surgery. And he discovered how vowels and consonants, the different phonetic categories, are encoded, or we could just simply say coded, by recording the brainwave activity from the person's brain. The major part of the brain that we hear in is in the temporal lobe. That's kind of this area just right above, kind of in the area above the ear here in the skull. So we have a temporal lobe on this side and temporal lobe on the other side too. And this paved the way for hearing devices designed to develop and solve the cocktail noise problem. So he was able to, with his computer technology and electric engineering technology, interpret, decode what the brain and recognize vowels and consonants and recognize actually people's voices. So based on his research, understanding how the brain processes speech and how the brain can pay attention to specific, he's developed what he calls the cognitive hearing aid. And I'll show this and play it a little bit. So similar to Dr. Wang's device, the cognitive hearing aid uses neural networks and machine learning to decode the speech heard by the listener. They're just taking different approaches and writing different computer programs. So each of these are kind of on track in discovering similar kinds of things, and hopefully we'll develop a hearing aid. So I'm gonna, the next slide here, I'm gonna just talk about this cognitive hearing aid for just a second. It automatically separates out the voices of multiple speakers in a group. Next, it compares the voices of each speaker to the brain waves of the person wearing the hearing aid, this cognitive hearing aid. And then the speaker whose voice pattern most closely matches the listener's brain waves is amplified. So he's able to, having an electrode connected to the brain, he's able to tell which voice I'm actually listening to or you're listening to. And he connects this to a hearing aid. And that helps the hearing aid focus on that voice. So hopefully this will make sense to you. So here he's got an electrode hooked to this person's brain, and it's doing all sorts of processing. and so it's listening to the speaker, but it's figuring out who, of multiple speakers and background sounds, it can figure out which one of these people to focus on by being hooked into the hearing aid. So let me play this.
How to be a shepherd. Being a shepherd can be a lot of fun, especially
You're hearing
when
two
you know how
voices,
to
the
do
male
it.
and the female voice.
Shepherds can
Now
be found all over
the
the
brain's
world.
going to focus
Any
on
place from the deserts of
difference between
Israel
breeds
to
before
highlands
making a
of Scotland.
choice.
the male voice and
The
see how
breed
it's
of a dog
amplifying
can
that
have
male voice.
significant impact on its
Many
personality,
shepherders like to
as well as its size,
If you want
health,
to do this,
and
it
required
would be best
maintenance.
to move to Wales or
For
Scotland.
example,
If you
long-haired
want to live in
breeds,
the United
like
States,
collies,
Now he's going to listen
to
to the
Idaho
female.
or
they
Wyoming,
require frequent.
buy a sheepdog.
If you do not have
Some sheepdogs are better than others. You would do best to look on a dog market online or see it
And
here on
notice
the
how
computer.
it decreased the unwanted sound and increased the wanted sound. So, perhaps in 5 or 10 years, we may have what's called a cognitive hearing aid. So in summary, I'm going a little over. So, listening and noise is a difficult task. Hearing aids and implants are helpful, but have limitations. Human and animal studies are increasing our understanding of how the brain processes speech and noise, and is beginning to be introduced into hearing instruments. And hearing aids and implants are helpful, but have limitations. So by the use of deep learning and machine language and neural networks, we'll probably be able to incorporate these into hearing aids and help us hear better in noise. So with limited time, we have time for questions and answers.
Perfect. That's great. Thank you very much. Makes me really sorry I wasn't there for all of these presentations at the convention, because it's such interesting presentations, and you did a great job of kind of boiling them down and making them understandable for those of us that are not scientists.
Hopefully.
There's a couple of questions, and I apologize. Our suite is now being vacuumed, so I hope that there's not too much noise in the background here. The first question, will there ever be hearing aids that make speech clearer?
Yes, I do think, and I think with the last two presenters, Dr. Wang and Dr. Masgarani, and other researchers that are trying to develop these devices using what we call artificial intelligence, specifically deep learning or machine learning, using neural networks and other kinds of technology. And as we better understand how the brain, interprets this coded message from the inner ear, I think that we will. Now, there are now going to be 2 hearing aids on the market that are using artificial intelligence. One of the hearing aids from, what can I think of the company? Widex, is kind of making decisions, like a chess player. So when a person goes into different listening environments, such as noisy restaurants, and then listening to TV, and then listening to a group of people, and then to one speaker, it's learning from the person how they're adjusting their smartphone to adjust their hearing aid. It's learning to better adjust the hearing aid in these different environments than the person wearing the hearing aid than manually adjusting. So that's one thing that's coming along. Now, the second one, Starkey Hearing Aid, is coming out with a new hearing aid that will come out here beginning September or October. And it's built in artificial intelligence, although it's not really focusing so much on clearing up speech as it's got sensors in the hearing aid, so that when you stumble or fall, it will call maybe a family member and alert them that you've fallen.
Wow.
Or you can have it send information to the doctor's office. And then you could communicate via the hearing aid and directly with the hearing aid, the smartphone, with a physician or a family member to see if you need help. It can also measure, I think, blood pressure, heart rate, body temperature. So there's a number of sensors built into that particular hearing aid, all using kind of machine learning to detect these kind of things. So I think, yeah, this is a hot item. So how soon, I can't tell you exactly, but both Dr. Wang and Dr. Masgarani expressed hope that this would be coming and be able to be built into hearing aids and cochlear implants, the technologies that they're working on.
Mm-hmm. It does seem with AI that capability is just right around the corner.
Well, I think it's more around the corner than we think. As I mentioned, deep learning, some say this is a subset, and machine learning and deep learning, these are subsets of artificial intelligence. And these programming capabilities are much faster to write the code compared to what we call the basic foundation of artificial intelligence. If you have Alexa on your smartphone, it's amazing how accurate it, if you speak clearly, how accurately it converts speech into text.
Mm-hmm.
So the speech recognition abilities are really increasing. Now, it's not really that good at noise yet, but I think from Dr. Wang's research and Dr. Mascaroni's research, these technologies are going to be built in. And perhaps even from Dr. Lee's research, some of his findings may be built in.
Lisa asks, have you heard about the Bose Hearphone? It's a lightweight collar with earbuds. You remove your hearing aids, and it pairs with my iPhone, so I can control it from there or from something on. She says, I have moderately severe hearing loss. While I hear my frequency loss is below all letters, the Bose earphone are significantly better than my very expensive hearing aids in all noisy situations. And I can make out accents much better as well.
Yes, and I'm not real familiar with, I haven't done a lot of research and read up on the particular Bose technology, but they're using a little bit of what we refer to as digital noise reduction. So what it's trying to do, they have written programs that are trying to detect a speaker's voice versus noise and subtract that noise out of the speech. And for some, it is quite helpful. And for others, not so helpful, but that's great that it's helpful for you. Oop, I'm not hearing you right now.
I'm sorry. Has the research by Dr. Mascaroni been published in a publicly accessible place? Mary would like to read it.
Yes, one of the articles I referred to was published in 2012. The next one was 2014, and then he published another one or two. And he's got a great number of research publications. If you go to Pubmed.org, PUBMED.org, and type his name in, and maybe put his name in quotes. You can turn up some research articles. Some he's the lead author, and other articles he's one of the maybe 5 or 6 researchers included in the research. So that's one way to find specifically his research.
Okay, maybe we can even get him to write an article for Hearing Life.
That would be great.
Yeah.
You know, just might do that.
Yeah, that'd be great. Gloria Matthews asked, I'm 35 and into technology. How can I follow speech to text technology as well as advancements made in hearing technologies? Is there one kind of go-to place to kind of keep up on all of that, Perry?
Come every year to the HLAA convention. Send me double the check, Nancy. No. It's a great place. A lot of the research, a lot of folks and technicians that are developing technologies for persons with hearing loss come and exhibit some of their devices, which oftentimes you can try out. And this last year, there were some amazing, there were 6 or 7 really great new technologies I was not aware of. And so that was fun to explore. Some of these are smartphone apps. Some of these are fairly inexpensive devices. Some of these are future devices that they're kind of exploring and wanting, trying out with people that are attending the convention. So that's one place. That's the greatest place. Now, I'm an audiologist, so I go to the American Academy of Audiology convention every year. And there's a lot of new technologies there that I can learn about and explore and presentations on. And I assume you're kind of interested in the acoustic technologies, is that correct? correct? Speech technologies.
Speech to text is what she said, and also just the advancements in hearing technologies, whether it be, I'm assuming she's referring to hearing aids as well as assistive devices as well. You know, it's one of those things that we kind of try to tackle here with our new website. We are hoping to have a section on emerging technologies, but we just don't have a staff right now to keep up on everything. But we do have, you know, technology articles in Hearing Life as well.
Yeah, this is one of, you know, I Google a lot of stuff, but, you know, you kind of have to be like a librarian to know the correct terms to put in, because so many items turn up, and trying to find specific articles that come up are sometimes challenging, because when I type in speech recognition technologies, lots of different things turn up that aren't even related to what I want to, you know, learn about. I'm trying to think of some blogs out there that might be helpful, but I would keep in tune with HLAA. You might go to hearingreview.com. And a lot of hearing aid, the introduction of new technologies and new discoveries are published there in very brief articles. So hearingreview.com.
Okay. The site that you mentioned earlier, Perry, was at Pubmed, MED. .org. Okay. Maybe we can try to corral all of these great sites and post them on our webinar replay page. I'll try to remember to do that. We have time for one more question, I think. This one from Russell. He says, interesting research, but what is being done to improve directional mics? Seems like this could result in good results in a relatively short time. Seems to me that today's directional mics are easily overwhelmed in really noisy environments. Good question.
Yeah, well, you know, all of the hearing aid industry manufacturers continue to work on this, on directional microphones. And, you know, when we look at some of the studies on animals, you know, that are good at directional detection, you know, all of the engineers look at those studies and try to incorporate what they learn from those studies into the technology. Part of the problem is, you know, hearing aids are small, and trying to get a very tiny little microphone that fits into these, you know, we keep shrinking the size of the hearing aids, and we're able to do it because basically you're putting computers into the hearing aid, into hearing aids, and we keep shrinking the size of that little computer we tuck inside a hearing aid.
Mm-hmm.
I think a lot of this is, we're going to have to use deep learning, and maybe the smartphone will do some processing connected to the hearing aid. Might be one of the things that I think in the short term might be used.
Mm-hmm. PC asked about where patients can get to try devices or become part of the studies. Coming to the HLAA convention once again is a place where you can try all of these devices. You'll never see so many gadgets under one roof. But if you're talking about any kind of medical research going on, HLAA recently partnered with Research Match. And you can find information about that on our website under Make an Impact. So if you go to hearingloss.org and go to the Make an Impact tab, you will see more information about that. That's a place where you can explore what research is going on and possibly one day even participate in a study. Anyway, I think we have to call it a night. It's 9 o'clock according to my watch. And thank you, Perry, very much. And if I haven't thanked you enough for not only doing this webinar tonight, but it was Perry's idea for the whole research symposium on this topic of listening and noise, and corralled all the presenters, invited them, worked with the presenters to make sure that they were on board, and it really was a fabulous research symposium. I've seen great reviews about it from people that were in attendance. So thank you, Perry, very much for doing that. And
well, thank you for trusting in that proposal that I sent. And it was just an area that research symposium, I went through all the symposium, couldn't find one on this topic. So well, we need one on this.
You're right. You're right. We were overdue for this topic. It's definitely one we need to keep an eye on as well as technology changes and so forth. So thank you again for presenting tonight. And thank you, Donna, for providing CART. Good night, everybody.
Good night.